Dr. Rico here. This is an introduction to my mini course, Robotic Planning and Kinematics. The syllabus link and notes are in the description. All right, so let's talk about the problem setup and modeling assumptions for motion planning via decomposition and search. The sensor-based planning problems we studied in the previous chapter are also referred to as closed-loop planning problems in the sense that the robot actions were functions of the robot sensors. This is sometimes called reactive control, okay? The loop here is the following. The robot moves, then it senses the environment, and then it decides how to move again. In this chapter, we begin our discussion about open loop planning. By open loop, as compared with sensor-based and closed loop, we mean the design of algorithms for robots that do not have sensors, but rather have access to a map of the environment. This is sometimes called a type of deliberative control. Open loop and closed loop strategies are synonyms for feed-forward and feedback control. As in the previous chapter, we are given a workspace that is a subset of R2 or R3, often just a rectangle, some obstacles, say O1 to ON, a start point and a goal point, and a robot described by a moving point. As in the previous chapter, we defined the free workspace, W free, to be the entire workspace minus, set minus, the union of all of the objects. See figure 2.1 here. We continue to postpone more realistic and complex problems where the robot has a shape, size, and orientation. So we see here we have a point where we start, a point where we go. The robot will be represented by a point. This is our workspace. The free workspace is the portion of the workspace that does not include these obstacles. Maybe this is obstacle 1, obstacle 2. Okay. Our task is to plan the robot motion from the start point to the goal point via a pre-computed open-loop sequence of steps to be executed. We want to design a motion plan under the following modeling assumptions. Robot assumptions. The robot has the following capacities. It knows the start and goal locations and knows the workspace and obstacles. World assumptions. The workspace has the following properties. The workspace is a bounded polygon. There are only a finite number of obstacles that are polygons inside the workspace, and the start and goal points are inside the workspace and outside all obstacles. It is instructive now to compare these new robot and world assumptions with the ones in the previous chapter for sensor-based closed-loop planning. The similarities are the following. 1, the robot is still just a point. It has no size, shape, or orientation. And 2, the robot's motion is omnidirectional, i.e. the robot can move in every possible direction. The differences are the following. 3, the robot has no sensors, but rather knowledge of the free workspace. And 4, planning is now a sequence of pre-computed steps projecting into the future, whereas before, sensor-based algorithms are a policy on how to deal with possible obstacles encountered along the way. And we don't know what they're going to be. All right, 2.1.2 polygons. In these notes, a polygon is a plane figure composed by a finite chain of segments called sides or edges closing in a loop. The points where the segments meet are called vertices or corners. Polygons are always assumed to be simple, i.e. their boundary does not cross itself. Programming-wise, it is convenient to represent a polygon by a counterclockwise ordered sequence of vertices. It is our convention not to repeat the first vertex as the last. Okay, that is one convention. We won't use it. As illustrated in figure 2.1, we already saw, this chapter assumes that the workspace is a polygon that each obstacle is a polygon, i.e. a polygonal hole inside the workspace, and that the total number of vertices in workspace and obstacles is n. Runtime of an algorithm. In this chapter, we will study the time it takes for a motion planning algorithm to run, called its runtime, rather than just the length of the path it produces. The runtime of an algorithm is given by the number of computer steps required to execute the code. For the purposes of these notes, we assume that addition, multiplication, and division of two numbers can be performed in one computer step. Similarly, we assume a single computer step is required to test if one number is equal to, greater than, or less than another number. The runtime of an algorithm is a function of the size of the input fed to it. If the input has a size n, for example, the input is a polygon with n vertices, the runtime is a function f of n. Counting the exact number of computation steps can be a complex endeavor, and so we instead focus on determining how the runtime scales with n. Rather than saying an algorithm takes exactly 5n squared plus 4n plus 1 computer steps, it is customary to drop all constants like the 5 and the 4 and the 1, and all lower order terms like the n and the end of the 0 term, and simply report the runtime as O(n squared). Formally, the big O, that's what it's called, big O notation, is defined as follows. Definition 3.1. Given two positive functions, f of n and g of n, of the natural numbers n, we write f is an element of O of g if there exists a number n naught and a positive constant k such that f of n is less than or equal to k g of n for all n greater than or equal to n naught. Intuitively, if f is an element of O of g, then we are saying that the function f is less than or equal to the function g up to a multiplicative constant and for large n. In other words, when n gets large, g grows at least as fast as f. For example, in figure 2.2, the function f of n grows linearly with n, and g of n grows with the square of n, and we have f an element of O of g. Taking a look at this figure here, we see that f of n is actually greater than g of n for small n, but we don't care about small n. We only care about how the function grows for large n. So we can say that g of n bounds f of n, at least in its growth, even though f of n happens to be larger than g of n for small n. So this is an introduction to big O notation and polygons and the workspaces, sort of setting up the problem for us. And in the next lecture, we'll check out a little bit deeper how to decompose a workspace into polygons. See you next time.